Okay, so this talk is going to be about certain misconceptions that people have regarding limits, and these are misconceptions that people generally acquire after. So these are not the misconceptions that people have before studying limits. These are misconceptions you might have after studying limits, after studying the epsilon delta definition. And I'm going to describe these misconceptions in terms of the limit game, the prover-skeptic game of the limit, though the misconceptions themselves can be don't depend on your understanding of the game, but to understand exactly what's happening, it's better to think of it in terms of a game. Let me first recall the definition. So limit as x approaches c of fx is a number L. So c and L are both numbers, real numbers. F is a function, x is approaching c. And we say this is true if the following is true. For every epsilon greater than 0, there exists a delta greater than 0, such that for all x which are within delta distance of c, fx is within epsilon distance of L. Okay. Now, how do we describe this? So how do we describe this in terms of a limit game? Yeah.
So the skeptic starts off with the first part of the definition.
The picking the epsilon. Okay, that's the thing written in black. What's the skeptic? Like, what's the goal of the skeptic?
To try and pick an epsilon that would not work.
So the overall goal of the skeptic is to try to show that the statement is false.
Yeah.
Right? So in this case, the skeptic should try to start by choosing an epsilon that is really, the idea of the skeptic wants to choose an epsilon that's really small. What is the skeptic trying to challenge the prover into doing by picking the epsilon? The skeptic is trying to challenge the prover into trapping the function close to L when x is close to c. And the way the skeptic specifies what is meant by close to L is by the choice of epsilon. Okay, so the skeptic is, when picking the epsilon, the skeptic is effectively picking this interval L minus epsilon to L plus epsilon. Okay, and basically that's what the skeptic is doing. The prover is then picking a delta. What is the goal of the prover in picking the delta? The prover is saying, here's how I can trap the function within that interval. I'm going to pick a delta, and my claim is that if the x value is within delta distance of c except the point c itself, so my claim is for any x value there, the function is trapped in there. So the prover picks the delta, and then the skeptic tries to meet the prover's claim or test the prover's claim by picking an x, which is within the interval specified by the prover, and then they both check whether fx is within epsilon distance of L. If it is, then the prover wins, and if it is not, if this is not less than epsilon, then the skeptic wins. Okay, so the skeptic is picking the neighborhood of the target point, which in this case is just an open interval of radius epsilon. The prover is picking the delta, which is specifying the neighborhood of the domain point, except the point c itself. So it's an open interval centered at c, excluding c, and then the skeptic picks an x in the neighborhood specified by the prover, and if the function value is within the interval specified by the skeptic, then the prover wins. Now, what does it mean to say the statement is true in terms of the game?
So it means that the prover is always going to win the game.
Well, sort of. I mean, the prover may play stupidly. The prover can win the game if the prover plays well. So the prover has a winning strategy for the game. Okay. So the statement is true if the prover has a winning strategy for the game. That means the prover has a way of playing the game such that whatever the skeptic does, the prover is going to win the game. And the statement is considered false if the skeptic has a winning strategy for the game, which means the skeptic has a way of playing so that whatever the prover does, the skeptic can win the game. Or if the game doesn't make sense at all, maybe the function is not defined on the immediate left and right of C. The function isn't defined, then we cannot even make sense of the statement. So either way, if the skeptic has a winning strategy or the game doesn't make sense, the skeptic has a winning strategy or the game doesn't make sense, then the statement is false. If the prover has a winning strategy, the statement is true. So with this background in mind, let's look at some common misconceptions. Okay. Is this here? Okay. So let's say we are trying to prove that the limit as x approaches 2 of x squared is 4. So is that statement correct? The statement we are trying to prove?
Yes.
That's correct. Because in fact, x squared is a continuous function, and the limit of a continuous function at a point is just a value at the point, and 2 squared is 4. But we are going to now try to prove this formally using the epsilon delta definition of limit. Okay. Now, in terms of the epsilon delta definition, or rather in terms of this game setup, what we need to do is we need to describe a winning strategy for the prover. Okay. So we need to describe delta in terms of epsilon. So what the prover essentially, the only move the prover makes is this choice of delta, right? The skeptic picked epsilon, the prover picked delta, then the skeptic picked x, and then they judge who won. So the only choice the prover makes is the choice of delta, right?
Exactly.
So the prover has to specify delta in terms of epsilon. So here is my strategy. My strategy is I'm going to choose delta as I, as the prover, is going to choose delta as epsilon over the absolute value of x plus 2. Okay. Now, what I want to show is that this strategy works. So what I'm claiming is that so let me just finish this and then you can tell me where I went wrong here. Okay. So I'm claiming that this strategy works, which means I'm claiming that if the skeptic now picks any x, which is within the delta distance of x, within the delta interval of x, within delta distance of 2, the target point, then the function value is within epsilon distance of 4, the claimed limit. That's what I want to show. Now, is that true? Well, here's how I do it. I start by taking this expression. I factor it as x minus 2 x plus 2, and absolute value of product is product of absolute value, so this can be split like that. Now, I say, well, we know that absolute value x minus 2 is less than delta, and this is a positive thing. So we can write this as less than delta times absolute value x plus 2, right? And this delta is epsilon over absolute value x plus 2. So multiply by absolute value x plus 2, absolute value x plus 2 cancel, and we get epsilon. So this thing equals something, less than something, equals something, equals something. You have a chain of things. There's one step where you had less than. So overall, we get that this expression, this thing, is less than epsilon. So we have shown that whatever x the skeptic would pick, the function value lies within the epsilon distance of the claimed limit, as long as the skeptic picks x within the delta distance of the target point 2. So does this strategy work? Is this a proof? What's wrong with this? Do you think there's anything wrong with the algebra I've done here?
Well, we said that
So is there anything wrong in the algebra here? This is less than delta. Delta is epsilon. So this part seems fine, right?
yeah.
There's nothing wrong in the algebra here. So what could be wrong? Our setup seems fine. If the x value is within delta distance of 2, then the function value is within epsilon distance 4. That's exactly what we want to prove, right? So there's nothing wrong sort of this point onward. So the error happened somewhere here. What do you think was wrong here? In this step, the strategy choice step. What do you think went wrong with the strategy choice step? Well, okay, so in what order do they play their moves? The skeptic chooses epsilon, then
the prover chooses delta.
Prover chooses delta, then
the skeptic has to choose the
x value. So when the prover is deciding a strategy, when the prover is choosing the delta, what information does the prover have?
He just has the information on epsilon.
Just the information on epsilon. So
in this case, the mistake was that because he didn't know the x value yet.
The strategy cannot depend on x.
Yeah.
So the prover is sort of picking the delta based on x, but the prover doesn't know x at the stage when picking the delta. The delta that the prover chooses has to be completely a function of epsilon alone. Cannot depend on the future moves of the skeptic. So the prover cannot read the skeptic's mind, okay, and doesn't know what the skeptic plans to do. So that's the proof. So I called this, can you see what I called this?
The strongly telepathic prover.
So, you know what I meant by that? Well, I meant the prover is sort of reading the skeptic's mind, right? It's called telepathy. Okay, so get the next one. Okay, so this one says there's a function defined piecewise. Okay, it's defined as gx is x when x is rational and 0 when x is irrational. So what would this look like? Well, pictorially, there's a line y equals x, and there's the x-axis, and the graph is just the irrational x-coordinate parts of this line and the rational x-coordinate parts of this line. So it's kind of like both these lines, but only parts of them, right? Now we want to show that limit as x approaches 0 of gx is 0. So just intuitively, do you think this statement is true? As x goes to 0, does this function go to 0?
Yes.
Because both the pieces are going to 0. That's the intuition. Okay. So this is the proof we have here. So the idea is we again think about it in terms of the game. The skeptic first picks the epsilon. Okay. Now the prover has to choose the delta. But there are really two cases on x, right? X rational and x irrational. Mm-hmm. So the prover chooses the delta based on sort of whether the x is rational or irrational. So if the x is rational, then the prover just picks delta equals epsilon. And that's good enough for rational x, right? Because for rational x, the slope of the line is 1, so picking delta as epsilon is good enough. For irrational x, if the skeptic's planning to choose an irrational x, then the prover can just choose any delta actually, like just fix a delta in advance, like delta is 1 or something. Because if x is irrational, then it's like a constant function, and therefore like for any delta, the function is trapped within epsilon distance of the claimed limit 0. Okay? So the prover sort of makes two cases based on whether the skeptic is going to pick a rational or an irrational x, and based on that, if it's rational, this is the prover strategy. If it's irrational, then the prover can just pick any delta. So can you tell me what's wrong with this proof?
So he's still kind of basing it on what the skeptic is going to pick next.
Okay. So it's actually pretty much the same problem in a somewhat milder form. That is, the prover is sort of making cases based on what the skeptic is going to do next and choosing a strategy according to that. But the prover doesn't actually know what the skeptic is going to do next. So the prover should actually have a single strategy that works in both cases. So cases will be made to prove that the strategy works. So the prover has to have a single strategy. Now in this case, the correct way of doing the proof is just the prover can pick delta as epsilon, because that will work in both cases.
Exactly.
Yeah. But in general, if you have two different piece definitions, then the way you would do it is you would pick delta as the min of the deltas that work in the two different pieces, because you sort of want to make sure that both cases are covered. But the point is you have to do that, take the min and use that, rather than just say, I'm going to choose my delta based on what the skeptic is going to move next. Okay. So this is a milder form of the same misconception that was there in the previous in the previous example we saw. So this is what I call the mildly telepathic prover, right? The prover is still behaving telepathically, predicting the skeptic's future moves, but it's not so bad. The prover is just like making doing a coin toss type of telepathy, whereas in the earlier one, the prover is actually deciding exactly what X the skeptic would pick. But it's still the same problem. And the reason why people have this misconception is because they don't think about it in terms of the sequence in which the moves are made and the information that each party has at any given stage of the game. Let's do this one. So this is a limit claim, right? So it says that limit as x approaches 1 of 2x is 2. Okay? So how do we go about showing this? Well, the idea is let's play the game, right? So let's say the skeptic picks epsilon as 0.1. Okay? The prover picks delta as 0.05. So the skeptic is, when picking epsilon as 0.1, the skeptic is saying, please trap the function between 1.9 and 2.1. Okay, find the delta small enough so that the function value is trapped between 1.9 and 2.1. The prover picks delta as 0.05, which means the prover is now getting the input value trapped between 0.95 and 1.05. That's 1 plus minus this thing. And now the prover is claiming that if the x value is within this much distance of 1, except the value equal to 1, then the function value is within 0.1 distance of 2. So the skeptic tries picking a x within the interval specified by the prover. So maybe the skeptic picks 0.97, which is within 0.05 distance of 1. And then they check 2x is 1.94. That is at a distance of 0.06 from 2. So it is within 0.1 of the claimed limit 2. So who won the game? If the thing is within the interval, then who wins?
The prover.
The prover wins, right? So the prover won the game. So therefore this limit statement is true, right? So what's wrong with this as a proof that the limit statement is true? How is this not a proof that the limit statement is true? This, what I've written here, why is that not a proof that the limit statement is true?
Because it's only an example for this specific choice of epsilon and x.
Yes, exactly. So it's like a single play of the game, the prover wins. But the limit statement doesn't just say that the prover wins the game. It says that the prover has a winning strategy. It says that the prover can win the game regardless of how the skeptic plays. There's a way for the prover to do that. And this just gives one example where the prover won the game. But it doesn't tell us that regardless of the epsilon the skeptic picks, the prover can pick a delta, such that regardless of the x the skeptic picks, the function is within the thing. So that's the issue here. Okay. Now you notice, I'm sure you've noticed this, but the way the game and the limit definition goes, you see that all the moves of the skeptic we write a for all, right? And for all the moves of the prover we write there exists. Why do we do that? Because we are trying to get a winning strategy for the prover. So the prover controls his own moves, right?
Exactly.
So therefore, wherever it's the prover's move, it will be a there exists. Whereas wherever it's the skeptic's move, the prover has to be prepared for anything the skeptic does. So all those moves are prefaced with the for every. Okay, let's do one last one. By the way, this one was called you say you want to replay, which is basically just saying that just one play is not good enough. So if the statement is actually true, the prover should be willing to accept it if the skeptic wants a replay and says, I want to play it again. The prover should say, sure, and I'm going to win again. Right? That's what it would mean for the limit statement to be true. So let's do one last one. It's kind of pretty similar to the one we just saw, but with a little twist. Okay, so this one, let's see. We are saying that the limit as x approaches 0 of sine 1 over x is 0, right? So let's see how we prove this. So is the statement true? Well, do you think the statement is true? As x approaches 0, would a sine 1 over x go to 0? So here's the picture of sine 1 over x. Y-axis. And it has it's an odd function, and it has this kind of picture. So does it go to 0 as x goes to 0?
No.
No. So you say that this statement is false, but I'm going to try to show it's true. So here's how I do that. So let's say the skeptic picks epsilon as 2. Okay, and then the prover, so the epsilon as 2, so that's a interval of width 2 above the claimed limit 0. The prover picks delta as 1 over pi, and then whatever x the skeptic picks, right? So regardless of the x that the skeptic picks, the function is trapped within epsilon of the claimed limit. Is that true? Yes, because sine 1 over x is always between -1 and 1, right? And therefore, since the skeptic picks an epsilon of 2, the function value is completely trapped in the interval from -1 to 1. So therefore, it's import the trap within distance of 2 of the claimed limit 0, right? So regardless of what the skeptic does, right? So it's not just saying that the prover won the game one time. It's saying whatever x the skeptic picks, the prover can still win the game, right? So it's kind of regardless of the x the skeptic picks, the prover has chosen a delta such that the function is trapped. It's completely trapped. Okay, so it's not an issue of whether the skeptic picked a stupid x. So do you think that this proves the statement?
No, I mean in this case it's still dependent on the epsilon that the skeptic chose.
It's still dependent on the epsilon that the skeptic chose. So yes, that's exactly the problem. So we proved that the statement, we proved the thing from this part onward, but it's still, we didn't prove it for all epsilon. We only proved for epsilon is 2. And 2 is a very big number, right? Because the oscillation is all happening between -1 and 1. And if in fact the skeptic had picked epsilon as a 1 or something smaller than 1, then the 2 epsilon width strip would not cover the entire -1, 1 closed interval. And then whatever the prover did, the skeptic could actually pick an x and show that it's not trapped. So in fact, the reason why the prover could win the game from this point onward is that the skeptic made a stupid choice of epsilon. Okay. So in all these situations, all these misconceptions, the main problem is not keeping in mind the order in which the moves are made and how much information each player has at the stage where that move is being made.